both CFD and experimental techniques are used side by side to study such complicated flows. Now I'll just give a brief overview of turbulent flow simulations. So basically, turbulent flows consists of multiple length scales and time scales, and therefore they are very difficult to solve on a computer. And most often, you require supercomputers to solve the Navier-Stokes equations for turbulent flows. Now, there are several methods which are there. One is the direct numerical simulation, where you solve the Navier-Stokes equations without any modeling, and naturally it resolves all the scales, and the computational cost is very high, and therefore you cannot use this method for high Reynolds number flows. The practical flows are always at high Reynolds numbers in our applications, and therefore DNS is very restricted in such applications. Now, the next best thing is large simulations, which have evolved as a kind of partial answer to turbulence simulations. It's like you solve for some scales which are present in the flow and then model the other scales. So these large scales are solved for, and then you model the other scales, which means that they are slightly, or to a large extent, computationally cheaper than the DNS. Then also RANS is used for getting quick answers, where you solve an averaged form of the Navier-Stokes equations, and they are of course cheaper than the DNS and LES. So in this talk, I will focus on the DNS and LES results for some flows, which I will cover. Okay. Now, CFD has limitations in reaching high Reynolds numbers, in the sense that the detailed computations become very expensive even on the supercomputers. And for doing DNS, you need very high computing power, as also sometimes for doing LES. Okay. Now, just a quick word on turbulence modeling. So RANS is widely used by industry for solving compressible flows, where standard K-epsilon modules are used. But then there are many limitations, especially for compressible flows, while using this K-epsilon sort of model, especially when it comes to capturing the turbulence anisotropy at high Mach numbers. So it seems that either you do experiments, or if you want to do proper CFD, then you should do at least LES, if not DNS. Now, compressible flows have challenges because the flow velocities are comparable to or more than the speed of sound, and when they are higher than the speed of sound, then shocks appear in the flow, and also there can be shocklets, which are features of turbulent flows. That means near some eddies, or at the borders of eddies, adjacent eddies, there can be small shocks, even though in the entire flow there may be no visible shocks, but locally at the eddies there can be shocks. Then that is a very big challenge for numerical simulation. Then of course there are density, pressure and temperature variations all happening simultaneously in such a flow, as also viscosity and thermal conductivity variations. So apart from this, most compressible flows of practical interest have mixed supersonic subsonic regions, so which make the numerical study difficult. That means you have to specify boundary conditions very carefully, as well as inflow and outflow conditions. So during the talk I will elaborate more. So let's have a look at the governing equations that we are looking at. So continuity equation is given as the first equation, that is mass conservation, where you have the density, which is a variable, along with other variables such as velocity and pressure. So the other variables or the other equations which are relevant are the momentum equations or momentum conservation equation, which is the second one, and the third one is the energy equation. Now, this is one form of an energy equation, and these whole set of equations, especially the momentum and energy equations, are normalized, and which brings the non-dimensional parameters into the equations, such as the Mach number, the Reynolds number, and the Prandtl number. So all these non-dimensional parameters govern the flow, especially if you keep Prandtl number to be fixed, which is most commonly used, then the Mach number and Reynolds number are the ones which dictate or govern the compressible flow. Now, from these equations, which are the instantaneous flow equations, one can derive mean flow equations, which are basically the Reynolds averaged Navier-Stokes equations. So here you see the mean flow equations, and within the mean flow equation, namely the mean momentum equation, you have the turbulence, which is showcased by this Reynolds stress term. So this is the term which requires to be modeled when you are doing RANs. That means when you are solving for the mean flow, you have to solve or you have to model this term. So that is all that is done in turbulence modeling, and this is not trivial, especially for compressible flows. Even in incompressible flows, it is challenging for complicated flow situations such as separated flows, etc. Now, different kinds of closure models are there for RANs. I'll not go into this. These are some of the types of models which are there. Now, one also studies transport equation for Reynolds stresses. So this contains production term, then various diffusion terms, then the pressure strain term, which is given by this one, and dissipation terms. So then there is TK transport equation, which I will not go into. Now, the community who are involved in the turbulence research, and especially in compressible turbulence research, are involved in developing proper models for Reynolds stress equations, especially for the pressure strain correlation term. As also, there are huge efforts in developing SGS models, that is subgrid scale models, for the LES of compressible flows. Then study of shock turbulence interaction for external and internal flows using DNS and LES is the focus of many groups, including my group at IIT Kharagpur. Some of the examples are mentioned here, like compression ramp, impinging shock on boundary layer, jetting supersonic cross flow, etc. And sometimes it is important to assess how important are explicit compressibility effects in perspective of modeling of compressible flows. Now, also, compressible reacting flows are a hot topic, especially in regards to combustion in scramjet engines, for example, where combustion has to happen in supersonic speeds, and it's not a trivial thing, and that's why the scramjet engines have not yet been very successful, but work is still going on, and in near future we will see a proper scramjet engine which will be tested and so on. Then you have the computational acoustics area or aeroacoustics area, which is mostly related to the jet acoustics. So engines are producing jets which produce noise because of various vertical activities in the jet, as also shock turbulence interaction inside the jet and so on. Okay, so and encompassing all these activities, there is always a scope for developing new shock capturing methods and strategies. Okay, so I'll just skip all these literature reviews and compressibility effects part, and then go to the numerical methods that mostly will be used in this talk. So for LES and DNS, we use high order finite difference schemes having low dispersion and dissipation errors, which are necessary. So if you are familiar with CFD, or if you have done a course in CFD, you will know that dispersion and dissipation errors are very vital for turbulent flows. Then the second thing is that you need to have very good boundary conditions for compressible flows, especially that's tricky for aeroacoustics. So the aeroacoustics is a very much of an emerging area since last few decades, and lots of activity has been going on, and we have just stepped into this area in the last few years. So
Professor
yes,
Ghosh, your
yes.
voice is not audible.
Oh,
Your
can you hear
voice
me
is
now?
very poor quality or audibility.
Oh, should I log out and then log in again?
No, but I
Let
can
the
hear you
others can.
clearly.
Okay.
I don't know.
Can you?
I don't know if this problem is from my side or others can share their experience.
Uh, I can hear clearly.
Oh, okay. 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 So should I carry on?
Yes, sir. Yes.
Okay. Okay. Thank you. Okay. So let me just go through, get back once again to what I was talking about. I was talking about the boundary conditions, and especially they are very important for aeroacoustics. Then LES modeling is a huge area of research, and there are explicit subgrid scale models like the Smogowski model which are used, and also then there is a area of the implicit LES where you don't have to have any explicit subgrid scale models. So the implicit LES thrives on the fact that you use the dissipation of the numerical scheme to do your subgrid scale modeling. Okay. So regarding shock capturing, so shock capturing is required. So when you have shock in a turbulent flow, so the shock is a finite jump over a very small length scale. Okay. So to capture this or to keep this in the simulations, one method is to do shock capturing. That means you use numerical schemes which are dissipative and which capture the shock within within a couple of grid cells, within a couple of grid points, let's say. So there are different methods which are used for that. So these are some of the shock capturing schemes that are widely used, and we have used, for example, the bandwidth optimized weighted EMO scheme and TMO schemes for the DNS of shock turbulence interaction and so on. Then we have not explored this artificial diffusivity approach, so I will do that with a future student. Then the third approach is to do LES based on explicit filtering with additional adaptive filtering near the shocks. So I have explored this with my couple of students, and I'll show you some results based on that. Now for the DNS results that we are going to show, we have used these schemes, that is a fifth order compact finite difference scheme, upwind, which provides a small dissipation at the high wave numbers, and that is used for the convective terms, and then the sixth order compact central schemes are used for the diffusive terms. So for the time stepping, we use an optimized or low storage third order Ringo-Kutta method. So this is an explicit time stepping method, which means that we are relying on the CFL criteria for evaluating our time step. So the first flow that we are going to look at is the DNS of models and diffuser flows, which I did for the first time, and the results were published in Journal of Fluid Mechanics in 2014. So this was from my PhD thesis, basically. So these are the grid resolution which are given, and we have an incoming pipe flow which is turbulent at Mach 1.5 and 1.8, and these friction Reynolds numbers and isothermal walls. So at that time, we used 64 cores for simulating the model and 128 cores for the diffuser. and these took a lot of time for computing. Okay. So I'll just quickly go through the explicit filtering approach, which we use for the larger simulations. So it just means that we filter the Navier-Stokes equations using a properly designed filter, and that is it. So we don't use any other subgrid scale model. So if you want, you can look into it. The slides are there. Yeah. So if you look at the turbulence spectra, so this is where we are. If you look at the solid lines given in the spectra, as I am pointing out, so the solid lines are the DNS spectra, and the dashed lines are the LES spectra. So the expectation from a good LES is that it should follow the low wave number part of the DNS spectra very faithfully. So it is the case when you have good LES approach, and this is the case here. We have done numerous studies and found that our LES approach is good, as it follows the DNS spectra in the low wave number range. Okay, so these are some pictures from the DNS of nozzle and diffuser flows. So the bottom one is from a nozzle flow. So we are plotting the velocity fluctuations in the nozzle. So there is an incoming pipe flow coming in from the left and expanding in the nozzle, and this is how the turbulence looks like in the nozzle. Similarly, we have a diffuser, which means that there is a slight compression geometrically to the of the incoming pipe flow, and this is how the turbulence looks like in that diffuser. Okay, so recently we have done, so this was for the nozzle and diffuser with circular cross sections. So we have also explored planar nozzles, so which is very important for stealth applications. This is what I found out. Planar nozzles are becoming quite important these days, and therefore we decided to do LES of both asymmetric and symmetric planar nozzles, and this was done recently, and these are the parameters, flow parameters and domain lengths and etc. So what is more interesting are the results. So what we see are isosurfaces of the second invariant of the velocity gradient tensor, which roughly denotes the vertical or the vortices which are present in the flow. So this is the asymmetric diffuser, which shows that the turbulence decays as we go along the nozzle. The turbulence decays along the nozzle, and this is the symmetric nozzle, which shows again the decay of turbulence, but in this case, near both the walls, the decay happens more or less equally, while here near the straight wall there is a lesser decay. So these have been studied. So these we have studied for 2 Reynolds number. So you see the higher Reynolds number typically denotes the finer scales of turbulence. Okay. So we have also managed to do the DNS of such flows, and I will not go into that, just showing you some results. We have also done CD nozzle simulations, LES of that as well as DNS, and these are some of the results which show how the turbulence evolves in a, let's say, academic CD nozzle. So we have also done bell type CD nozzles, which are important for rocket applications. So which I will show later on. So this is one of the bell type nozzles, which shows the evolution of turbulence. Then these are all flows which do not have shocks. So I will quickly come to the flows which have shocks, and that will become more interesting. So recently with Mansi, I have studied high Reynolds number turbulence, compressible turbulence, and you can see how the flow structures look in a high Reynolds number turbulent flow, which makes it extremely difficult for doing very accurate measurements in an experiment. So numerically we are able to simulate even with the with the LES. The DNS is very difficult. We haven't been able to do it with our resources, we are doing it, but it has not completed. So the LES is giving us very good insights into the very large scale motions that are typical of wall bounded turbulence at these Reynolds numbers. So we have compared our results with the DNS and we find good agreement at the resolution that we have used. So we have also extended our work to so this is basically Mansi's work, ongoing PhD thesis. We have done this supersonic nozzles at high Reynolds numbers, and you can see how these structures evolve, the flow structures evolve in the nozzle if you consider a wall parallel plane. So I'll not go into deeper into these topics. So let's come to shock trains in ducts. So the students who are already studying gas dynamics, they will know that if you are subjecting a pipe flow or the channel flow to back pressure, you will have shocks in the flow. Now, when you study inviscid flows, then you have a single shock because there is no boundary layer in an inviscid flow. So then the solution which you have is a single shock, which is a normal shock. Now when you have boundary layer effects, that is there in a real life flow, then you have multiple shocks, which is popularly called a shock train. So a sketch is shown here where the boundary layer thickening results in presence of shock, and the shock structure will depend on many factors such as the Mach number, the Reynolds number, and what is called the flow confinement, that is the ratio of the boundary layer thickness to the height of the duct. Now, it is observed that not only one shock is present, but then subsequently expansion waves occur, which leads to an expansion region. Then another shock comes, then expansion, then shock, and so on. So there are multiple shock and expansion waves which are there, and such regions are popularly called shock trends. Okay, so I have listed here. So this has been very popular in the recent years, and it is now very busy activity area in compressible turbulence community, the shock trends in internal flows. Basically, because of the applicability of such problems in scramjet engines. So everyone who is doing proper compressible turbulence research around the world are have jumped into this area, and you can see a lot of studies in this area. Now we have published in 2017 in Journal of Turbulence this paper on shock train in a pipe flow. So without going into the details, so the Mach number is 1.7 and friction Reynolds number is low, and this is the flow confinement ratio. So the method used was LES using explicit filtering, and there was no additional filtering which was used. So these other methods have been standard in our group, and we will not go into that. And this is the resolution, a typical resolution used in the LES. Okay, so when you have a shock train, then if you look at an instantaneous pressure isosurface, it looks like this. So this is the inflow on the left. So there are subsequent or consecutive shocks and expansion regions in the flow, and this gradually diminishes, and we reach after a certain length a region where no further shocks can occur because the Mach number has reached something like a close to sonic value. So then the rest of the region is just a turbulent flow region without any shocks. So this is how the shock train looks like in a turbulent flow. This is the instantaneous picture, and this is how, if you cut at different cross sections, the shocks look like. So these are broken shocks, not like a one in a laminar flow. So in a laminar flow, you would expect concentric circles, but in a turbulent flow, because of the presence of flow structures, the shocks are broken, and they are ever changing with time. Okay, so this is a mean flow picture for the mean pressure and density, for example, and this is how the mean centerline density looks like across the shock train. as well as the mean centerline pressure. So these are standard results which we have verified with qualitatively with experiments and so on. This is how the Mach number looks like. Okay, and what is more interesting is how the turbulence evolves across the shocks. So the turbulence is amplified as it crosses the shock train, and then again there is a relaxation. This is a Reynolds stress which I have plotted, and again there's amplification, then there's a relaxation, and so on. So this is quite difficult to model when you have such complicated shock turbulence interaction, and this is a centerline behavior, and this is as we move closer to the walls. Okay. So we have very large compressibility effects in terms of pressure dilatation, correlations, etc. near the shocks. And we have also studied the low frequency oscillations of the shock train in terms of pressure traces, and I'm not going to that. And what is the take home message is that the shock trains exhibit broadband oscillations, in the sense that if you do a spectra or a power spectral density of the pressure, then you will find multiple peaks at lower numbers, lower frequencies. So this low frequency behavior is not only concentrated at a particular wave number, at a particular frequency, but at multiple frequencies. So this makes it very difficult to model such flows in terms of a single mode. So we have recently done DMD analysis, dynamic mode decomposition of this phenomena, and we have gained very good insights on this. I will not go into that. So let me just quickly go through the rest of the talk, because I guess I'm running out of time. So we have recently been able to do shock train simulations in channel flows using third order bandwidth optimized Rono scheme. So this code was developed in our group by Sandeep Kumar, who was my second PhD student. And then this was extended to, so I'll not go into this. So recently we have extended this work to DNS and implicit LES of shock train in channel flow using a high order TINO scheme, targeted TINO scheme. So these are very state-of-the-art shock capturing schemes which we have included in our code, and the results are very encouraging if you look at this. Just 1 minute on the shock train in CD models, which we have done with our LES code, but here we have also implemented adaptive filtering, which is supposed to be active near the shocks. So this provides a very comprehensive shock capturing method. This is an alternative method compared to the shock capturing schemes. So these are the results from those that work, which got published in Journal of Turbulence last year. And so we have done many things in that area. So the last topic of today that I'm going to focus on is compressible jet simulations, which we have done using a code which was developed by Pat Thakur and myself recently. So this is a round jet, cross section of a round jet, and you can see the incoming flow, and then it starts transitioning into turbulence, and then you have the turbulent jet. It's an LES done at a very high Reynolds number of 4,50,000 with 5 million grid points. Okay, so these are the near wall, the near field pressure isosurfaces, which shows the near field noise that we are going to predict from, which comes automatically out of a compressible flow solver. We have also done far field mass, which we are doing right now. So the far field mass computation involves solving the flow equations as an LES in the near field, and then using linearized order equations in the far field. So all these are compressible calculations, and just showing you how the far field acoustics of a jet looks like. So this is again pressure isosurfaces. So this is the near field, and this is how the acoustic waves propagate from the near field into the far field. So we have done this for the subsonic case as well as supersonic case, and we are about to submit a paper on this. So we have done extensive simulations with my student Asmita, who is currently working as a PhD student with me. So Asmita has also done compressibility studies of round jets. So we found out that at high Reynolds numbers, there is no study of compressibility effects on round jets. So we systematically did a study of round jets at different Mach numbers, starting from very low subsonic values to transonic and then high supersonic values, and we are looking into the compressibility effects. The first thing that you note is that the growth rate of this is diminished as we reach supersonic Mach numbers, and this is a well-known fact, but we are going into the details such as how the potential core expands as you go along to higher Mach numbers and so on. Okay, so one work which we did was a very extensive DNS of relatively low Reynolds number subsonic round jet, and these are the beautiful pictures that emerged from the DNS. That is a vorticity magnitude field, and this is a dilatation field. Okay, and this was published in 2023 in JFM. This is a very nice paper if you want to look into. So the basic thing was that we have done flow topology studies because we have DNS data. So we could do flow topology studies. I will not go into the details. You can look into the details if you want. So other work focuses on impinging round jets. This is Swagatika's work, and also other PhD students are carrying on this work. We have done dynamic mode decomposition of such fields, and this was published in the AIAA journal recently, 2 years back. Okay, so I'm more or less done. So just summarizing what I talked about, you got a glimpse of how important DNS and LES, that is direct numerical simulations and larger simulations of shock-free compressible flows, are in terms of providing valuable database for turbulence modeling. Now, nowadays with the advent of AI, AI is widely used for developing Reynolds stress models or turbulence models. And again, for such activities, AI needs a lot of data sets which are very accurate. So doing such simulations is very, very necessary to generate a lot of data sets to develop good turbulence models, which then can simplify the task of doing numerical simulations. Now we are far away from developing a viable model for compressible flow. So there, if you ask all the experts, they will differ regarding what is a good turbulence model for a compressible flow. But these flows are very important for industrial applications, and then the need for modeling is very, very important, very much appreciated. So many groups are working on it. Some are doing simulations, some are into the act of using the simulation data to refine models. Then comes the challenge of shock turbulence interactions, and there we have a lot of activity in DNS and LES area, which tends to mainly focus on the change in turbulence structure across the shocks, and also the low frequency oscillations which are there in shock turbulence interaction problem. So this can be different in different flows. In external flows, you have some kind of oscillations. In internal flows, you have other kinds of oscillations, and so then it is quite complicated for even just for simplistic predictions. Okay. Now, LES of computational air acoustics rather is a very important area if you want to develop silent flight, where jet acoustics is one of the dominant noise sources, or jets are one of the dominant noise sources, and therefore high order methods and very accurate prediction of jet noise is very important. So yeah. So the other ongoing work is on areas of reacting flows using different kinds of models. So I am now focusing on Flamelet models with progress variable approach, and then LES of shock train at pipe in a pipe at moderate Reynolds number, and so on. So the list is there for you to see. and that is more or less done. So I have been supported by AIDB over the years, and then SERB, two projects have been there, and other projects are in the pipeline. So I'm grateful to my PhD students who have completed the work and who have contributed to this seminar. Based on their results, I have given this talk. Sushila, then Sandeep, then Parth, then Swagatika, Agni, and all. And then there are the recent PhD students whom I have in my group. And so we use mostly right now the Param Shakti High Performance Computing Center in IIT Kharagpur, and our own departmental cluster in our department, so which we have developed from different projects. And some of the computations in the beginning, I mean, when I joined IIT Kharagpur, were done in the Supercomputing Center in Munich. So I'm grateful to all these organizations who have provided resources for the computations. Okay, thank you very much for your patience, and I hope the talk was interesting.
Thank you, sir. Thank you for your wonderful presentation, taking us, giving us an opportunity to delve such a deep into your topic. I hope all the participants have also gained knowledge from your wisdom. Sir, you have very aptly described from starting from the very beginning, the very basic of the TFDs, discussing about the continuity equations and all the momentum equations. Then you have already discussed about the LES and DNS simulation techniques. From then you have jumped to shock capturing, shock training, and whole lot of compressibility studies. I will say the whole picture in the compressibility studies. You ended up with round jet mechanisms. Sir, I will like to take this opportunity, like in any of the participants, having any question for our sir, they can go ahead, or otherwise we will move to our next segment, and then we'll try and bridge this two topics where we are trying to integrate our compressible flows with the dynamic statics related systems. How do we bridge and move to flow to function, integrating our compressible flows with our rotodynamic systems? So any questions from the participants?
Good afternoon, sir.
Yes, good afternoon.
Please hand over to Professor Ghosh. Hello.
Yes, sir. Somnath Ghosh, sir, Dr. Somnath Ghosh, sir, is already available with us. You can go ahead with your query, sir.
Sir, recently I have started to do something in this area. I have very little knowledge about the incompressible flow field model, etc., etc. But however, I have started to do something. What I have done recently, this is a flow field model of a flapping wing. So in this regard, I have developed a model using ANSYS Fluent, and I got the results. But my next attempt is to do a theoretical model, and I want to develop a computerized code without any commercial software. So in this regards, which book do you want to refer, sir?
Oh, okay. So it depends on whether you want to do finite volume simulations, because I have talked about finite difference based codes. Now, if you want to do finite volume simulations, then there are many books like the Charles Hirsch book, and then there are some other common books like Anderson's book is also a good one. I mean, the old one, but a good one. So Charles Hirsch has a good book, yeah. And if you want to do finite differences, then the book of Parvez Moin, that is Engineering Numerical Analysis, is the one which is a good starting point. Yes.
Sir, in my model, uh, this is incompressible fluid. I have taken low Reynolds number. So is it necessary to, when it is
Yes.
necessary to consider the high Reynolds number as well as turbulent incompressible fluid, etc., etc. For a flapping wing, uh, uh, for low Reynolds number cases, in compressible fluid we have considered. So when your model is suitable for such cases?
I don't think the flapping wing will have high Reynolds number or will reach very high Mach numbers. I mean, it depends on the application. So if you are talking about insect flight and other things, so then it's always low Reynolds number and low Mach number. So then the incompressible model is perfectly okay. So there is no need for compressible models.
Okay.
So if you find an application, I don't know about any applications where flapping wings are used in very high speed flight. So if you come across that, then you can use compressible flows. I mean that model you can use.
So low
Otherwise, the incompressible model is perfectly okay.
perfectly okay.
Yeah, the low Reynolds number is because you are looking at the insect wings probably. If you look at aircraft wings which are flapping, then the Reynolds numbers will obviously be high. So then you have to go for high Reynolds number flows simulations.
Okay. Thank you, sir.
Okay, welcome.
Any questions from other participants? Okay then, sir, please be with us. Thank you again for your such an
Yeah, sure. Thank you.
experience. Please be with us. Sir, I would now request
Yes.
Professor Dr. Haraprasad Roy, sir, to please start your presentation by sharing your screen. Yes, sir. Your screen is visible to us.
Okay.
Okay. Thank you, sir. You can start your presentation, sir.
So myself, Professor Haraprasad Roy from NIT Rourkela, Department of Mechanical Engineering. Here we'll start our next presentations after Professor Ghosh. So coming to our presentation, before starting the presentations, I want to share a few lines about the Institute of Engineers, since the webinar is arranged by the Institute of Engineers. So my students, Sipana Jogandar, will read the slide about the activity of Institution of Engineers, IEI.
Good evening, sirs. Good evening, everyone. My name is Jugandhar. I am the research scholar under Professor H. Roy, sir. So I just want to explain about the Institution of Engineers. So generally, the Institute of Engineers was established in 1920 and headquartered in Kolkata, and it is the largest multidisciplinary professional body for engineers, which encompassing 15 disciplines with over 2.6 lakh members. And incorporated by Royal Charter in 1935, it provides professional, technical, and research support to government, industries, and academia through 124 centers in India and 6 overseas chapters. Recognized as a scientific and industrial research organization by the Government of India, Institute of Engineers India promotes R&D and offers grants to UG, PG, and PhD scholars. It also represents India in the International Professional Engineers Alliance in INTPEA and awards the PE certification. It is also located in NIT Rourkela. So I am giving it over to my professor. He will explain further.
Thank you, Sipana. So coming to the presentations, so my presentation comprises two parts. As the webinar is related to rotor-dynamics, so my presentation will focus on the rotor-dynamics part. So, but entire presentation is simply a textbook material. I do not do not include any research topic here. So for easy understandings, so my presentation comprises two parts. First is viscously damped single degree of freedom systems, and later on the idea of viscously damped systems into the rotor-dynamics. So first is I'll start explain what is viscously damped systems as well as their mathematical modeling. So coming to the viscously damped systems, the damping means it's the resistance provided by the opposes the motions. Damping modeling of damping may be done in various ways. So viscously damped, structural damping, Coulomb damping, many types of damping we can give a mathematical representation only. So in viscously damped systems, this means it is the damping provided by a viscous fluid. So ideal example of piston cylinder arrangement. A piston is moving into the cylinders surrounded by viscous fluid. In viscously damped systems, modeling is very easy. That's why everywhere we will prefer such type of damping. And equations of motion provided by the viscously damped systems, there are two ways of modeling. First is the complementary parts or free vibration based on the homogeneous equations. Another is the force vibrations considering the particular integral. Okay. Come to the viscously damped systems model is done where the viscous damping force Fd is proportional to its velocity. Fd is equal to Cx dot. C is the constant of proportionality. It is called damping coefficients. So if we consider a spring mass dashpot systems, single degree systems having mass m, spring stiffness k, and damping coefficient c. So equation of motions is given by mx double dot plus cx dot plus kx is equals to f of t. Ft is the force given to the system. So this is the differential equations. The solutions of the differential equation will give you the response to that systems. The solutions may be obtained by two has two parts, as I told, complementary functions considering the homogeneous parts, when right hand side will make it to be 0, and considering the right hand side to be non-zero, then it is called the particular integral. So first, free vibration studies or free vibration modeling of the single freedom system is done by considering the homogeneous part mx double dot plus cx dot plus kx is equal to 0, and characteristic equations of this equation of the differential equation is formed by converting its differential equations into algebraic equation by considering a form x is equal to e to the power st, where s is the constant, and by considering these assumed functions, the character equation will be mx square plus cs plus k is equals to 0. It is a algebraic equation, second order quadratic equations. Solutions of these second order equations, algebraic equations, S12 is equals to minus c by 2m plus minus root over c by 2m a whole square minus k by m. So this root, using this root, we can obtain the solutions of these equations. X is equals to a e to the power s1t plus b e to the power s2t. So s1, s2, we have a common term minus c by 2m. If we take it out, so ultimately we can rewrite it e to the power minus c by 2m t in whole into a e to the power root over c by 2m whole square minus k by m plus b into minus e to the power minus of that. So in these equations, if you see, there is a factor multiplied to that whole part e to the power minus c by 2m to t. This is the exponentially decaying functions. So this pattern of the solutions x will have a decaying factor, but the inside the term there is the radical. radical sometimes becomes positive, real, sometimes becomes imaginary, sometimes becomes zero. So depending upon that roots, values of the roots, real, imaginary, or zeros, these pattern of solutions can be obtained. So damping, depending upon the nature of the systems, so the systems may be defined as the oscillatory, non-oscillatory, etc., etc. So when the radical becomes real, that time it is called overdamped systems. So there is no oscillations. When radical becomes imaginary, oscillatory systems will be there. And there is a transition between oscillatory and non-oscillatory when the radical becomes zero. So it is a very important thing when the radical becomes zero. Based on that, we can obtain a important parameters that is called damping ratio. This is the C by CC. When C by 2m whole square is equals to K by 2m, that times damping coefficient is termed as CC. CC is equals to 2 root Km, and damping ratio is the C by CC. So using this damping ratio zeta, we can again write the equation in the form of zeta and omega n. So ultimately, we can obtain the different cases of solutions. Overdamped case when zeta is greater than 1, underdamped case zeta is less than 1, as well as critically damped zeta is equals to 1. Overdamped case example is door closer. Underdamped case, many examples when vibratory systems, and critically damped system example is the shock absorber. Okay, so this is the basic idea of the free vibration of a single degree of freedom systems. Okay, this is the when it is when the systems is oscillatory, that time decaying pattern is logarithmic, and based on the logarithmic decrement, we can also obtain the nature of damping or type of damping of the systems. Okay, chalo next slide. Chalo. Logarithmic is over. Coulomb damping also it is based on the when the damping between this object and surface is dry surface. The damping between the dry surface. Viscous damping, it is a viscously body is surrounded by viscous plate. When the body is moving on a dry surface, that time is called the Coulomb damping. The Coulomb damping model can be done in this way. So a spring, a body is vibrating on a supported by a spring, and based on that we can develop the model. Chalo, next slide. So coming to the force vibration. So force vibration of the systems is done considering the particular integral. Particular is particular integral when we consider the right hand side ft. So if ft is a harmonic sine or cosine function, the solutions of the four harmonic equations is very easy. Depending upon the excitation, we can consider a response pattern. So x small x is equal to capital X sine omega t minus phi, where capital X is the amplitude of vibration and phi is the phase angle. By putting these assumed functions into the differential equations, once again we can obtain a algebraic equations, and we can obtain the solution of capital X f by m k minus m omega square plus ic omega. And separating the real and imaginary part, we can obtain the capital X mod of x as well as phi is equal to tan inverse root over tan inverse b by a phase angle as well as amplitude we can obtain. Okay. So for further concise representation, we can use non-dimensional pattern, etc., etc. Okay, so if it is a damped systems, the response as well as phase are shown here. So response at resonance response become finite, unlike the elastic cases where the resonance response becomes infinite. Okay, frequency response curve. So this is here. Characteristics. Next. Frequency response characteristics means when the off resonance zone then there is a finite response, resonance zone, which is higher response. Depending upon the damping, the resonance amplitude is defined. Acha. So here is the important figure is shown. It is the vector representation of different forces. So as we have seen, the differential equation have three components of forces: inertia forces, dissipation forces, as well as spring force or restoring forces. So restoring forces kx, dissipation forces c omega x, as well as inertia forces m omega square x. So kx and m omega square x, they are acting opposite to each other, and but the c omega x, it is in quadrature. So kx and c omega x perpendicular to each other, but however the m omega square x is opposite to kx, and this is and opposite directions. So rest portions we have joined by using parallelogram theorem. So we can obtain the phase angle, and the force Ft is measured from after joining the kx and m omega square x. So it is over. So next we'll share another slide which shows the analysis of brief discussions about the rotor-dynamics. So rotor is a long slender body mounted by two or more numbers of bearings. So in rotors has two speed. One is the rotational speed about its own axis, as well as the speed of the bend plane. This is called whirling speed. So rotational energy as well as the vibrational energy arises in the rotor shaft systems. So as rotational speed is much higher than the vibrational or whirling speed, that's the rotational energy much higher than the vibrational energy. Our aim is to reduce the vibrational energy of a rotor shaft systems. So rotor shaft, there are various types of rotor shafts: rigid bearing, rigid shaft, and semi-rigid and fully articulated systems. Next slide. Based on the boundary conditions, rotor can be defined as simply supported cantilever or damped supported rotor also. So rotor applications, many rotor applications. Everywhere where the body is rotating, that is called rotor. Rotor may rotate about low speed, high speed. So depending upon the applications, the body is the long shaft is rotating. So few applications such as wind turbine, turbine, helicopter, etc. So coming to the polymeric shaft, many applications of polymeric. What is the advantage of polymeric shaft? Polymeric shaft is a lightweight, magnetic signature free, and that's why it is used in underwater scooter, enigma rotor, ornithopter, and so on. Figures or slides shows the various applications of the polymeric shaft. Now coming to the simplest model of a rotor, that is called the Jepcot rotor. Jepcot rotor is a simply supported rotor. Total mass of the shaft is considered to be massless, and total mass is concentrated in the middle, and the rotor is a simply supported ends. So coming to the modeling of the rotor, Jepcot rotor model. So Jepcot rotor, first we will model the undamped Jepcot rotor, Next is the viscously damped Jepcot rotor. In undamped Jepcot rotor modeling is done based on the energy concept, kinetic energy as well as the potential energy. So rotor is primarily it is in rest positions. That time is shaft center at O and mass center at T, and shaft center C and the coordinates O are at the same positions. When it is rotating, that time it is deflected. So shaft center deflects from the origin O, and as well as there is a mass center is also deflected. The distance between the shaft center as well as mass center, it is called eccentricity. If the rotor is completely balanced, that time the eccentricity becomes 0. So due to the eccentricity, the shaft during rotations produces a centrifugal force and it causes a deflections to that shaft. So modeling of the Jepcot rotor is done by considering the deflections of the shaft center C, it is denoted by XC and YC, as well as the coordinate of the P or mass center XP, YP. The strain energy is the half K X C square plus YC square. However, the potential energy is calculated considering the coordinate of T, mass center, half M XP dot square plus YP dot square. So XP and YP can be converted to the XC, YC coordinate. So ultimately, we can obtain the kinetic energy as well as potential energy in terms of the coordinate XC and YC. Once we obtain the T and U, kinetic energy and potential energy, we can apply the Lagrangian when we can develop the equation of motion of an undamped Jepcot rotor. Mxc double dot plus Kxc is equals to Me omega square cos omega t. Next equation, Myc double dot plus Kyc is equals to Me omega square sin omega t. So this is the equation of motions of an undamped Jepcot rotor. Now coming to the viscously damped Jepcot rotor. So here we consider this rotor shaft is made of damped material, and damping nature follows the viscous pattern. Means viscous force Fd is equals to Cx dot. Once again, in the rotor shaft systems, there are two kinds of damping. It is non-rotating damping, another is the rotating damping. There are few parts which is not rotating, that is damping produces by their parts is the non-rotating damping, and rotor shaft, it is a rotating body and damping produces by the rotor shaft, it is called the rotating damping. So non-rotating damping, as the damping force is proportional to its velocity, velocity is the rate of change of displacement. So first we have to measure the displacement. So non-rotating damping, to consider the dissipation force. So displacement of the non-rotating parts, so it is calculated, measured from the inertial frame of reference. But while considering the damping from the rotating parts, so rotating damping, so dissipations and displacement of the rotating parts has to be calculated in rotating and rotational frame of reference. So in these two frame of reference, there should have some transformations. Otherwise, we cannot calculate the equations of motions. So there are two coordinate systems. X, Y is an inertial frame of reference. Zeta are the rotating frame of reference. The transformation between two frames are needed. These transformations give you the transformation, rotary transformation matrix R. So zeta is equals to R into XCYC. So once we obtain the rotational transformation matrices, this matrices is used to convert the dissipation energy of the rotary parts into the stationary coordinate. We can obtain the equation of motions or the viscously damped Jepcot rotor. Here we see that unlike non-rotating systems, here one additional terms arises, that is the omega related stiffness matrices. This stiffness matrices is Q-symmetric in nature, means off diagonal term arises, diagonal term zeros, and off diagonal term is Q is Aij is equals to minus Aji. Means off diagonal term are arises but opposite in sign. This matrices is known as the skew-symmetric stiffness matrices, and this is the speed dependent matrices. Omega is 0 when it is non-rotating systems. No matrices will vanish. For rotary systems, omega is non-zero. That time this matrix has to be considered. So using this equation of the motions, we can do the analysis of the rotor shaft systems. Come to the free whirling. So free whirling, likewise the free vibration of a vibrating systems. When we consider a rotor is completely balanced and considering the complementary function CF and making it to be based on the homogeneous equations, right hand side to be 0, we can obtain the analysis of eigenvalue analysis, or assume considering the assumed functions RC is equals to RC0 to the power ST, and we can obtain a characteristic equation as well as the solutions of the characteristic equations will give you the roots of the characteristic equations. This roots is a imaginary sigma plus minus I omega. Sigma indicates the real parts and omega indicates the imaginary parts. From the real part, we can predict the stability of the systems, and from the imaginary part omega, we can predict the natural frequency of that systems. So Campbell, two important things are two important plots which explains the nature or behavior of the rotor shaft systems. This is called Campbell diagram. Another is a decay rate plot. As the damped systems comprises two roots comprises two parts, sigma plus I omega. Sigma once in these roots depends on this spin speed omega, capital omega. So if sigma is plotted between sigma versus capital omega plot is the decay rate plot, as from real part indicates the decaying nature. So from that pattern of the plot, we can predict the systems is stable or unstable. So if decay rate plot exceeds the 0 line, that time system become unstable. If it is below the 0 line, systems is stable. Likewise, decay rate plot, Campbell diagram is the plot between the whirl frequency as well as the spin speed, small omega versus capital omega. So from this whirl Campbell diagram, we can predict the natural frequency or critical speed of that systems. So Jepcot rotor, as I told while modeling, there are 2 points C and P. C is the shaft center, P is the mass center. When the rotor shaft is rotating in a low speed, that time OCP line lies in a first quadrant, and C point is in between the O and P points, P point far from the origin O. But when the shaft is in critical speed, operating in critical speed, that time OCP makes a perpendicular formations. And when shaft speed is go on increasing supercritical region, that time what happened? P come closer to the O point, and P point becomes in between the O and C points. This phenomena is called the self-centering effect. Means this time shaft reflections again reduces and minimizes, tries to minimizes again. This is the mode shape of the rotor shaft system, rotating systems. As I told, rotor is rotating as well as it is whirling. So rotor deflections of the rotor deflected rotation of the deflected path is the whirling. Here are few mode shape how the rotor is rotating are shown. First mode shape, second mode shape, etc. There are two, obviously there are two modes, forward and backward. When the synchronous when this whirling speed is same as the spin speed, that is rotor shaft is rotating in a forward mode. When this whirl speed is opposite to that spin speed, that time it is a backward mode. But fast forward, fast backward, it is seen that there is in between maximum deflection is seen, no node in between. But in second mode, one node is found in between, means like in two ends there are deflection, zero deflection, as well as in between there is a zero deflection. So from that fast mode, forward and backward mode, we can predict the rotor shaft is rotating in which directions, same directions or opposite directions. Second mode is having a zero node at the in between. So this is the I conclude here. Before conclusion, I can share some remarks of the Jepcot rotor. So what are the conclusions? The Jepcot rotor is the simplest model, and in this model there are two likewise one physical and two one coordinate RC, as well as there are two physical auxiliary coordinate XC and YC. So depending upon the initial conditions, so rotor shaft may rotate having mode shape may form circular, elliptical or rectilinear depending upon the initial conditions. If the rotor shaft is rotating in a circular mode, as well as synchronous whirling conditions is imposed, the no point of the shaft is subjected to vibration, because if rotor shaft is circular mode, outer point is always remain outer, so no point is subjected to vibrations. Okay, thank you for your patience.
Thank you, sir, for your wonderful presentation. From the very beginning, we have discussed about the rotor system, rotor shaft system, how it is, and the solution techniques, various solution techniques of the rotors, starting from the viscously damped rotors, Jeffcott rotors, and you have aptly described about the various criticalities of the damping, and you have talked about the internal damping, the rotating damping systems. Now I open this forum for any questions that the participants may have. You can go ahead. Any participants having any questions, you can go ahead with the questions to Professor Dr. Haraprasad Roy, sir.
I think no questions.
Okay. I hope, sir, thank you again for your wonderful presentation. Sir, I would also like to invite Dr. Somnath, sir, Professor Dr. Somnath, sir. Sir, are you there?
Yes, I'm here.
Yes, sir.
Yes, I'm here.
So, yes, sir. Now I throw this forum open for the discussion, right? Like our topic was actually integrating the compressible flows and the rotodynamics for the next generation engineering. Sir, as you have aptly described about all the in details about the compressible studies and compressible flows. starting from the LES and DNS systems and the finite difference schemes using solution techniques, being the solution techniques, then the shock capturing, the shock train, and after followed by a wonderful presentation on the roto-dynamics modeling. So how do we can link and how do we can think of the effect of the compressible flows in the various dynamics to the rotor-dynamic modeling? Like going very specific, like how we can think of the effect in our stiffnesses, our damping, be it internal dampings or means rotating or non-rotating dampings. Yes, sir. Am I audible? Shall I repeat, sir?
Actually, so as Dr. Roy has authorized,
I hope my voice is clear now. More clear. Okay, sir. My
so well, moving on to concepts, let's say you have the concept. It's actually making, yeah. I don't know what other scale.
sir, my question was like, what? See, the purpose of this kind of webinars is that we discuss about
So
new
regarding
ideas.
just you find compressible flows in motors as well.
Do I need to log out and log in again?
Professor Ghosh, noise is not clear.
Sir, Dr. Haraprasad, sir, am I audible?
Yes, you are audible. You are audible.
Okay,
Professor Ghosh, your voice is not clear.
I'm also not able to hear.
Hello, am I audible, Professor Subho Mukherjee?
Yes, sir. You are audible from my end. I'm unable to listen. No, actually, I'm not picking up the voices for Professor Dr. Somnath, sir.
Actually, as per my knowledge, the low speed rotor then applicable, for example, turbine rotor and wind tunnel rotor or so other applications in daily uses. In such cases, incompressible fluid field model is not so important. But when we go for the rocket propulsion systems or very high speed, at that time, the fluid effect is also very much important, that depending upon the fluid flow model, so there will have some chattering effect as well as some instability effect. These things has to be considered, otherwise proper rotodynamics model analysis is not possible. And so fluid structure interaction effect, that time is very much essential. Otherwise, in daily examples, fluid structure interaction not so important. But when we will go for the aerodynamic model of the fluid, that time rotor speed has to be considered. Otherwise, you cannot have the perfect modeling of the fluid flow. But rotodynamic points of view, the fluid field effect is essential when it is used for rocket propulsion systems or very high speed rotor. You got my points?
Yes, sir. Means high speed application systems, the fluids interaction becomes prominent, and its effects can be taken into account.
Now, but when you go for the flow field model, that time always you have to consider FSI effect, considering the rotary effect of that fluid medium. Otherwise, your model aerodynamic model will not be complete.
Now, sir, as we are all aware of, right, in roto-dynamics modeling, we have also considered the various factors for roto-dynamic modeling. Can the compressibility factor or can bring in a rotodynamic instability? Whenever there is an interaction between we are trying to modeling a fluid film bearing that has a compressible flow of a gas. So can it bring up a rotodynamic instability? Induce a rotodynamic instability?
There is a term oil whip and oil whirl. That is a terminology.
Whip and yes.
So in such cases, fluid model is very much important. Otherwise, due to the fluid flow, there is some instability arises in the rotor subsystem, that is called oil whip. So flow field model is, or hydrodynamic modeling is also essential.
Okay. Now, likewise, do we have Professor Dr. Somnath Ghosh sir with us? Okay.
Yeah, I have to please see. Idea it should be okay.
Your voice is now little bit okay.
Okay.
Professor Ghosh.
Largely, my next question to our open forum is like, largely we find that our rotodynamic coefficients that we develop for bearings and seals, largely we can say they are not largely, actually they are typically, I will say typically modeled as frequency independent. They are modeled typically frequency independent coefficients. But does this compressibility factor or the studies related to the compressibility studies will affect the frequency dependency?
The discussion. So what which are we talking about?
Sir, I'm not able to pick up the voice. Sir, I'm not able to pick up your voice, sir. Sir, I'm talking about the frequency dependency of the rotodynamic coefficients. Like we cannot pick up your voice, sir. Anybody in this forum has got any questions or any? You can also join the discussion. The purpose of these webinars is that we discuss interdisciplinary. Yes. Go ahead, sir.
Yeah, actually, some of the discussions we're talking about which rotor, is it a helicopter rotor or is it a turbine rotor or Ramsey rotor? So it's a helicopter rotor. It's moving in high speed, especially at the tip. Then force oscillatory effects has to be taken into account. Then also for the turbine emissions. If you have gas turbines which are only for the aerospace applications like jet engines, compressibility, compressible flow has to be taken into account, and that is how it is done. Is this what you're talking about?
Sir, I'm just talking about like the rotodynamic coefficients for the bearings and the seals, which are typically modeled as frequency independent uh, formulations, using frequency independent formulations. But does a compressible flow, including integrating a compressible flow interactions, means flow interactions, really keep it frequency independent, or means what will be the frequency dependency in that case?
I'm able to hear. So I'm able to hear.
Okay, okay, sir.
That's working today. So next question.
Now, anybody has got any questions, you can come up with in this forum. We have largely discussed about. Yes, yes, sir. Sir, can anybody confirm whether my voice is audible?
Your voice is clear.
Okay, okay, thank you, thank you. Actually, I'm also actually I'm very tense that I'm not picking up Professor Dr. Somnath Ghosh sir's voice actually. Okay, let it be. It will be, it has been a very good interactive session to all the esteemed guests. That yes, sir. So it has been a very interactive, great interactive session, I will say. Actually, the idea of this kind of webinars is like we come up with interdisciplinary research topics, and we get to develop new ideas where we can go for the research in the future itself. So today's topic were related to the compressible flows and the rotodynamics applications where we can use for the next generation's engineering itself is a huge topic itself. Both the topics takes into huge effort uh, individually, and integrating these two, it's a huge task. Again, it's a very good presentation, and I would like to thank for beautiful presentation from both of our esteemed guests. I would also like to thank Professor Dr. Somnath Ghosh sir for joining us and delving and giving us this opportunity to delve such an in-depth in knowledge of the particular field. And also, I would like to thank Professor Dr. Haraprasad Roy sir, taking into consideration our varied audience. You have started from the very basic and have discussed about the rotodynamics application. Now, I would like to invite from IEI to talk about something about our today's webinar. And
Thank you, sir. Yeah, I will request our Deputy Director Technical Institution of Engineers, Mr. Sudeep Chakraborty, to deliver the vote of thanks if is available. Sudeep sir, are you available?
I would request Sudeep sir to go ahead with the vote of thanks, and it had to be followed by vote of thanks and a concludatory remarks from me and all our esteemed guests.
Very good evening.
No.
So
Yes, sir. Good
myself,
evening.
myself Sudeep Chakravarti, Deputy Director Technical from the Institution of Engineers India. So we came to the end of a very interesting session. And as we come to the close of this enriching session, I am glad to present the proposal vote of thanks on behalf of the Institute of Engineers and as well as the Institute of Engineers at Kolkata, IIM. First of all, I extend my heartfelt gratitude to our distinguished speaker, Dr. Somnath Ghosh and Dr. Aurobhushan Roy, for their highly informative and thought-provoking presentations. Our sincere thanks to Dr. Shubha Mukherjee for skillfully moderating the session and guiding the technical discussion. We also thank all participants for their keen interest and energy, which made this event successful. I thank all of you once again and look forward for your participation in our future technical progresses. Also, I want to inform the participant here that those participants which want to enroll for the certificate of participations, they can do it by tomorrow midnight. After that, the link will expire and you will not be able to register for the certificate. So if you are interested in getting the certificate of participation, please do it by tomorrow. Thank you.
Thank you, sir. As it needs to be followed up with the vote of thanks from on the behalf of IEM team, I would like to formally express my gratitude towards our esteemed guests once again for their invaluable contribution in their fields in which they are a pioneer itself, and such an immersive experience taking us through this through their journeys. I would also like to thank our IEI coordinators for their tireless effort and time for managing all this platform for this online webinar. Live, I would like this live webinar series. Thank you for making this a memorable event. I hope sincerely that many of us has got some many ideas we were trying to find out, and I've also hoped that our esteemed guests are there for every moment for helping us. If anybody want to get in touch with them, they can. Thank you, sir. Thank you, Somnath, Professor Dr. Somnath Ghosh, sir.
सर वो जो एक व्हाट्सएप में आपने जो करेक्ट करके भेजा है कोलाबोरेशन नोट उसमें ही हम ये आपका बाकी करेक्शन करके आपको दे उसमें ना हाँ हाँ कर दे हाँ 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 ठीक
चलो
I think we are at the end of the session.
Yes.
Thanks all of you, all the panelists, the moderator, and all the participants, patient listeners who are there listening through the webinar, to our Deputy Director Technical giving the vote of thanks. And I like to end this session of the webinar and looking forward for future interaction and collaboration with your organization. Thank you all. Okay,
Thank
with
you.
this
Thank
I
you,
end
sir.
with
Thank
this
you.
I end the webinar. Thanks all.
Okay. Thank you. Thank you. Thank you all, sir.